Okay, so section 1.4, okay, deals with a matrix equation. So you've learned about a system of equations and how a vector equation is really equivalent to a system of equations. And now you're going to learn that a matrix equation is equivalent to a vector equation, which is equivalent to a system of equations. So a system of equations, you're representing it. You're learning to represent it as a vector equation, which you did in section 1.3. But then in section 1.4, you learn to represent a, a system of equations as a matrix equation. And in order to make this connection, I have this little example where I have a matrix A, okay, a matrix A times a vector X. So again, you have this matrix A times this vector X. And what are the dimensions on the matrix A? How many rows, how many columns for matrix A? Okay, so matrix A is good, everyone. Excellent. Matrix A is a 3 by 3, 3 rows by 3 columns. Now the vector X, what are its dimensions for vector X? What are the dimensions on the vector X? Good. Oh, good, everybody. A 3 by 1. So in terms of matrix multiplication, which is really what you're doing here, the book sort of doesn't discuss the idea until chapter 2, but you are doing matrix multiplication. Because the column dimension of row A matches the row, I should be more clear, the column number, the number of columns in matrix A is equivalent to the number of rows in the vector X. So you can multiply matrix A times the vector X, and the dimensions for the rows and columns for that product matrix is going to be a 3 by 1. How many learned that maybe in high school or in another class, how to multiply matrices? Okay, so many of you have seen that. Okay, good. Well, that's what we're doing here. So how do you multiply two matrices? And in this case, we're multiplying a matrix by a vector, but a vector is a matrix. You use what's called, well, what's very common and what you've learned, or some of you have learned, is the row vector rule. So what you do is you start off taking the first row here and multiplying it by this column in the second matrix. So, and you do it, I want to say this the right way. You move across this row and down this column simultaneously. So, for instance, 2 times x1, that's right here, plus 3 times x2, that's right here, plus 4 times x3, that's here. So you use the row of the first matrix and multiply by the vector of the second matrix. And the second matrix is just one vector. Similarly, for the next entry, you're going to take the second row and multiply it by that column vector x. And so you're going to get -1 times x1. You move along the row and down the column. -1 times x1 plus 5 times x2 plus -3 times x3. Okay, and then similarly, to get the third entry, you multiply the third row by that vector, and you'll get these entries. This is how we multiply matrices using the row vector rule. Okay, are there any questions up to this step here? Please let me know if you're uncomfortable. All right, well, now you see what we can do is, well, let me ask you this. What, for this matrix here, how many rows are there? How many rows are there? Good. 3 rows. And how many columns are there? So I'm getting a difference of opinion. Some people are saying there are 3 columns. Some people saying there are 1 column. In fact, it's going to be 1 column, yes. Because look at what you're doing here. The first row here is the sum of 3 things, and that equals 1 thing. 2 times x1 plus 3 times x2 plus 4 times x3 is one entry. So we end up with a 3-by-1 matrix. Let's make sure everybody's comfortable with that. Is there anybody who's uncomfortable with that? Makes sense, Natalie. Good, good. All right. Well, now look at what we started off. We started off with this A times a matrix A times the vector x. And then we ended up with this matrix, but this matrix can be written as a linear combination of the vectors A1, A2, and A3. A1 and A2 and A3, by the way, are these column vectors. Okay, let me go ahead. You see here in the matrix A, we have these column vectors, A1, A2, and A3. And then in the vector X, we have the components X1, X2, and X3. Well, the matrix A times the vector X is simply a linear combination of these column vectors where the coefficients in the linear combination are the components of the vector X. You see, this matrix here can be rewritten as the linear combination of the column vectors of the matrix A. So I'm asking you, are you okay going from that matrix, that 3x1 matrix, to this linear combination? Are you all right with that? Benjamin's comfortable. Stefani's comfortable. Lewis is comfortable. Ariana, Samantha, wonderful, wonderful, wonderful. Good. Catherine is wonderful. Haley is. All right, good, good. So that means then that the matrix A times the vector x is equal to this linear combination of vectors. And this is the connection that I wanted to make for you, because well, I want to go now to the textbook, but may I go to the textbook? Is anybody still copying this, or are we good? Let me know when you're ready. All good? All right, all right. Well, so now I'll go to the book. Okay, and now they give this definition here. But in my view, it's not really a definition. It's just based on matrix multiplication. Yeah. Now this whole thing makes sense. This whole definition makes sense should make sense to us now. All right, and this leads us to a theorem in the book. Okay, this leads us to a theorem in the book, and they go through some examples that are pretty straightforward, but here's this theorem 3 in the book that makes the connection between a matrix equation, which is really now it's a system of equations, right? A matrix equation is a system of equations, can be written succinctly as that matrix equation. That matrix equation is the same as this vector equation, and the vector equation can be represented as the augmented matrix, that has columns A1, A2 up to AN. The columns of the column vectors A1, A2 up to AN are the column vectors of the matrix A. Okay, and so the vector equation can be written succinctly as this augmented matrix. You see, all these notations are very important in linear algebra. They're very important. Okay, and that's really, I mean, the big idea behind section 1.4. That's really the key idea. And it says theorem 3 provides a powerful tool for gaining insight into problems in linear algebra, because a system of linear equations may now be viewed in 3 different but equivalent ways: a matrix equation, a vector equation, and a system of linear equations. Okay, so are there any questions with that so far? All right, maybe give me a few thumbs up if you're comfortable. Good. Excellent. 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 Well, thank you, everyone. Well, there's another theorem here, another theorem that draws a connection between everything you've learned so far. If AX equals B, if that matrix equation has a solution, that means that the vector B is a linear combination of the columns of A. Further, the columns of A span the m-dimensional space Rm, and also A would have to have a pivot position in every row. These are all equivalent, logically equivalent. And these exercises, and that's why I like you working out the exercises. You know, I like you working them out by hand and taking your time and making these connections. So they give an example here where they give a matrix A and they give a vector B, and they say, is the equation AX equals B consistent for all possible vectors B, B1, B2, B3? And they do row operations. Okay. They row reduce this system of equations, and they end up with this echelon form of the augmented matrix. But it turns out that, again, I mean, here you have the bottom row where you have inconsistency for certain values of B1, B2, B3. The only way the system can be consistent is, I want to say this right. I want to say this the right way. The equation AX equals B is not consistent because some choices can make B1 minus a half B2 plus B3 equals 0. Where are they getting that? Well, this entry here reduces to B1 minus a half B2 plus B3. Okay, so the equation AX equals B is not consistent for all vectors B1, B2, and B3. Okay, and I want to say this the right way. One moment. I lost my train of thought here. Hold on. So if vectors, the entries in B, satisfy this restriction, then the system will be consistent. Okay, but this restriction here is a plane. You have B1 minus a half B2 plus B3 equals 0. That's an equation of a plane through the origin. Okay, I mean, you're used to, like, how many remember in maybe they've seen this, like equations of planes. You might have, and I'm going to stop very shortly because I know how many have seen like x plus 2y minus 3z equals 6, and hey, that's an equation of a plane? How many have seen that kind of thing in maybe a previous class, like calculus? Okay, you've seen that. So, okay, well, here instead of x, y, and z, they have B1, B2, and B3. Thank you, everyone. And so that's an equation of a plane. Okay, so that's your solution. Those are the vectors B that would make the system consistent. Those are the values of B1. If B1, B2, and B3 satisfy this restriction, the system will be consistent. So this is, I mean, really section 1.4, what it does is it makes the connection between a matrix equation, a vector equation, and a system of equations. And that's what 1.4 is about. Okay, and so are there any questions on that? Okay, let me go ahead and stop the recording.